I'm Sergii Strelchuk, and I would like to tell you and share some of the insights that I've been working towards with my colleagues when we apply quantum algorithms to problems in computational genomics. So let's start with a little bit of motivation. So what I call quantum pangenomics, it can be sort of traced back to, well, to genomics. So I guess it's not difficult to convince yourself or to motivate that genomics is a transformational technology. It's at the heart of our understanding of function of biological systems and disease. And pangenomics recently has become a kind of an important next step in our understanding in this journey of trying to understand how human software, human code, genetic code works. And it's the kind of approach that naturally incorporates genetic variations and of humans, of pathogens, of various organisms. And it comes with its interesting opportunities and challenges. So building and analyzing pangenome is computationally intensive, and quantum computing may offer prospects of speeding up some of those key tasks. So it will enable us to derive a more precise and less biased description of genetic variation, and also do some tasks that will be kind of very important upstream when we do drug discovery or personalized medicine and whatnot. So why not genomics? Why pangenomics? Why there's such a recent interest in pangenomics? Well, because the standard reference represents just a single instance of a human genome, and pangenomics allows us to store and analyze the genetic diversity across individuals and populations, avoiding the bias and kind of incompleteness of a single reference. So using pangenome instead of genome improves identification of genetic variants and disorders. And currently, the uptake of this tool, these ideas is rather slow because it's limited by classical software limitations, but also computational problems that are often intractable or not so easily tractable. So there are several steps when you work in this field of pangenomics. So first one is you have to compare and do multiple sequence alignment of genomes. Then you want to represent this alignment in a graph with nodes representing sequence fragments as below. And then you want to traverse through paths through the graph that represent new potentially new genome sequences. So these are the kind of steps that are very similar to ordinary genome assembly. And there's been a major milestone reached recently in 2023. The Human Pangenome Consortium published its first draft human pangenome. It's a data structure that incorporates information of 47 individuals, and it creates this sort of reference that allows us to reason about genetic variation that doesn't come predominantly from one, but incorporates this wide variety of human diversity. And I think they want to extend it to several hundred individuals in the coming years. So we are in the we're at the cusp of really interesting transition from kind of a data structure that is very biased towards a single human to a data structure that naturally incorporates variation. There are other interesting challenges in genomics. One of them I would like to highlight is biosecurity. We had a lot of learning to do during COVID, and I think we know that perhaps similar pandemics may strike us, and our ability to quickly sequence, analyze, and derive meaningful insights from data becomes vital. And one of the difficulties is, of course, it comes with various computational bottlenecks. And we hope that there are some ways of speeding up some of the data processing tasks using quantum computers. So my interest and my engagement with this area started with this Quantum for Bio announcement. In 2023, I believe, they issued an interesting call asking the question whether we can develop new algorithms to deliver quantum advantage for health, for human health. And I was very lucky to receive funding from Wellcome Leap as part of this program. And we assembled a remarkable team of across a number of institutions, primarily based in Cambridgeshire, University of Cambridge Department of Genetics. My recent home in Department of Applied Mathematics and Theoretical Physics. Now I moved to the Department of Computer Science in Oxford. I work very closely with wonderful colleagues at Sanger Institute, European Bioinformatics Institute, and many colleagues across the globe in Australia, in Melbourne, and in Kiev, Ukraine. So we are looking at various challenges, and our broad goal is to identify which problems allow have of the type of low data, high compute, and where quantum computing can naturally become useful in this space. And as a test bed, we don't work with sort of abstract synthetic data. We want to think about data sets that originate from, they have a biological origin. So one such example is we want to say we want to work with COVID and the S gene in particular. We see that it's highly variable, and we want to perform certain data, so certain kind of algorithmic tasks that relate to this S gene. They have to do with phylogeny and building kind of a history of mutations of this gene. And broadly speaking, I've been working in this space with my bioinformatician colleagues for over a year and a half. And I can tell you there are a lot of new exciting results and developments, and I can broadly break them down into four categories. So there are two major research directions which naturally arise from this work. One has to do with data encoding, another one has to do with optimization algorithms, and in particular quantum optimization algorithms. And we can also classify our current findings into two categories, ones that have practical potential, which is a sort of near immediate practical potential, and the other one has more of more theoretical significance, where currently we don't see any near-term advantage, but once quantum computers become big and powerful in the hopefully not so far future, we will be able to use them to do more sophisticated things. So I guess one of the issues that often is kind of swept under the rug when we focus on quantum algorithms is the data encoding. So what we want to have an efficient and scalable method to encode genomics data for quantum systems. The reason why this is a problem, or one should really deeply care about it, is because if you're not careful, the quantum circuits that encode information, classical data, into quantum states can be ridiculously long, completely negating any prospective advantage that you can get when you then feed this quantum states to your quantum algorithm and do something on top of it. So it pays to really do well at this stage. And when it comes to genomic data, it's not just encoding a random string into a state. We know there's some lower bounds on performance of this. Strings are very far from being random. But not only we want to encode the string, we want to preserve some of the key properties of this. The encoding should preserve key properties of the strings. For example, if you have two strings that are close in some distance, and in genomics people use added distance rather than having distance, then the corresponding quantum states should be close in fidelity in this case. So let's say you have two strings here. The added distance is 2 because you can delete A from the first position and append A from the second sequence to the second sequence at the end. And you want the inner products, you want the fidelity or some measure of closeness of the strings to be proportional to the added distance in the space. So that's very important for genomics. And if we want to have, we want fidelity to be close to 1 when added distance is close to 0, meaning you don't have to modify one string too much in order to get to the other string. So if fidelity is close to 0, then we can conclude perhaps that the added distance is close to the length of sequences, meaning they are effectively unrelated. So we have to keep all these things in mind. And as part of this big consortium, we've been thinking about two different ways of encoding. One is so-called tensor network approaches that allow us to optimize qubits, number of qubits and depth of the circuit, of an encoding circuit. And another one, which curiously has been mentioned in one or two previous talks, is to do with kind of machine learning approaches that allow us to extract essential data, biological essence of data, and then use that to in some sophisticated mapping from this feature set to set of quantum states. So in genomics, we have some extra information that we can use when we encode data. So we are not just faced with a bunch of random strings which we are forced to encode. We have quite a lot of possibilities which have been very little explored until recently. There's another facet to this, to quantum algorithms in genomics, and that's that many wonderful problems in genomics are known to be NP hard if phrased rigorously mathematically due to combinatorial explosion in complexity. As the problem becomes bigger and bigger, there's simply too many possibilities to consider in order to get to the answer to the ground truths. So what we decided to do, we tried to look at genome assembly, because it's a very seminal example of biological problems. And it is a sort of space where we see some potential for quantum algorithms. So if you think about genome assembly, you think of having a large set of relatively short reads from a genome. Think of a big string chopped up into small pieces, and you get to see some subsets of these pieces. And you want to process them into an assembly graph where vertices are associated with DNA subsequences and edges indicate the neighboring subsequences. And then you end up having kind of really complicated graphs, actually, as you see in the upper right corner. And what you want, really, you want to kind of flatten this graph. You want to walk through this graph in a certain way so that you end up having one long string that's kind of linear. And resolving these tangles, we call it tangles, is a very difficult problem. And in fact, in the 90s, people in classical bioinformatics space, they sort of gave up on this problem. And instead, when you're faced with this kind of an onslaught of complexity, you just try to get more data about the problem and possibly simplify the problem a little bit, get better heuristics. So what we found that there is a way of approaching this problem from an entirely different angle. We can phrase it as a QBO, so-called quadratic unconstrained binary optimization instance. And similarly, as one would represent, classic Charles-Sesmal problem. And then we can feed it to either quantum annealers, or perhaps compile them into the QAOA Hamiltonians, which then will be subsequently solved by circuit-based models. I should mention that this is a very general framework, and algorithms that to follow individuals through a pangenome graph, they operate in a similar kind of way. So assembly and traversal pangenome graphs they're not too dissimilar. As part of our journey, we also looked at some theoretical advances. So it's very important to be honest and to look at when quantum algorithms can work and where they are unlikely to provide an advantage. And having this kind of horizon scan, it was immensely valuable because it allowed us to identify the general directions where we see real prospects of quantum computing, both in a classical, in a practical side, as well as in the more theoretical side. So what we found that there are, if you just apply Grover naively or directly to the problem, you're not going to get a lot of advantage, because Grover is doing better than classical in an unstructured search space. But very often in genomics, you have a lot of information about your sequences and states, so many other methods, like dynamic programming style methods, work a lot better for pairwise alignment in particular. And what we see, I guess let me just briefly talk about sequence alignment. So one of the key fundamental problems that need to be solved before you reap any benefits kind of upstream, when you talk about personalized medicine and all this wonderful new technologies, you want to solve a sequence alignment problem. So you want to align two strings, minimizing its edit distance. And pairwise alignment is a very easy and straightforward problem. And initially, when we started, we thought, well, maybe there are some exciting new algorithms, quantum algorithms, that could genuinely speed it up. So we found that pairwise alignment is already very efficient. However, the multiple alignment, the multiple string alignment, multiple sequence alignment is a far more complicated problem. So it scales for strings of size n. If you have k strings that you want to align, it scales as n to the power of k. And it turns out that by carefully combining classical techniques with some Grover-esque search techniques, you can achieve speedups. And this is something that we will publish very soon. But you can break the classical, well-known classical bound on the multiple sequence alignments case. Often, when you're faced with large number of strings, k in principle is, could be hundreds, and n could be also hundreds. So, we're not really having a lot of, even with a quadratic speedup, you're not getting very far from classical possibilities. So perhaps it's worth considering other proxies for multiple sequence alignment. Perhaps there are problems, the problem formulations which once stated, once solved, could imply something about the multiple sequence alignment. And one such problem is so-called the center string problem, where you have a bunch of strings, think of them as kind of little ropes, and you want to find another string that is for which the pairwise distances to all the other string is minimal. So again, this problem is hard in general, and there may be some nice speedups, and it is indeed possible to find speedups for the dominant part d to the power d to the d plus 1 using classical techniques. But this space largely is very open, and a lot of new ideas of how one can combine classical and quantum algorithms are welcome. So far, we've seen a fruitful coexistence and collaboration between classical and quantum algorithms in the space of variational methods, but I think there is more to explore when we pair very established classical techniques, optimization techniques, or perhaps just dynamic programming style techniques with quantum subroutines. And this is a kind of a paradise for people who like theoretical computer science, because there are a lot of problems that imply something useful for multiple sequence alignment and so on. So the problems I listed here are in the order of being more and more sort of esoteric. So the closest string problem is perhaps the most common, and then you get all the way down to the distinguishable string selection problem, where it becomes very kind of esoteric, I should say, for lack of a better word. So all of these problems are NP hard, even for binary alphabets. But I think given that subtly different structure of questions that are being asked, there is some possibility of having heuristics that work better for some problems, but not the others. So this space has largely been unexplored from the quantum side of things. And I think there are a lot of really good possibilities to think about these problems from the point of view of different distances, not just Hamming distance, but Levenstein or unweighted edit distance, general weighted edit distances, and so on. But also one could explore these problems through the lens of parameterized quantum complexity and quantum property testing, where this is again a very recent, people started very recently just started to make some inroads into the quantum parameterized complexity, and I guess quantum property testing has been around for a while, but again it hasn't been so well developed in the case of string problems. One of the things that is vital when we talk about optimization is how do we represent the problem in this optimization space. The one strategy I alluded to is called QUBO. It's perhaps the simplest and the most studied choice of encoding, where each QUBO variable is assigned a qubit, and then this somehow is mapped to the execution graph of an annealer of sorts. It turns out that there are many other interesting encodings. There are encodings that may achieve super polynomial compression of your problem, so that you will one qubit or several qubits could buy you several perhaps an order of magnitude of those variables, QUBO variables that you can encode in them. So those encodings are largely unexplored, and even when they're introduced, there is no real guarantee, or there are very few performance guarantees when it comes to these encodings. So I think this is one of the really fascinating and very little explored areas of how do we given a biological problem, how do we efficiently encode it in such a way that it still retains its biological significance while allowing us to explore the optimization of the corresponding optimization task on not just on quantum annealer, which is well suited for this, but also in terms of circuit-based model, QAOA. So normally the rather unfortunate feature is that when you compile QBO into QAOA, you experience quadratic kind of blow up. So the more efficient you are on the QBO side, the fewer qubits you'll need on the quantum side. So for biological problems, the curious thing is that there are several ideas that you might want to consider exploring. So think of perhaps not just exact one-to-one encoding, but what if you just try and approximate the kind of, you want to construct an approximate encoding of a problem, and then perhaps this encoding will give you too many answers, and then you'll have potentially a way of classically post-process those answers and weed out those that are biologically insignificant. So as I say, lots of space for creativity and opportunities here. There's also kind of a practical dimension to this research. So often we're asking, how do we evaluate real world performance of our algorithms? And if you are theoretical computer science, well, you think, well, we have a runtime guarantees. We have worst case performance, and if worst case is perhaps not too useful, because it just shows that there is an input to a problem which will force the algorithm to perform this many steps to get to the answer. But in reality, we're faced with biology is not just full of random strings. When we see some kind of a sequence, how do we know? Is it a worst case instance, or is it an average case instance? So maybe on average, algorithms will do a lot better, quantum and classical algorithms, when it comes to the real data. But perhaps even an average case guarantee is not enough. So Harry Berman recently introduced this concept of queasy instances, which is rather curious, because often we're interested in solving a specific problem instance rather than finding sort of universally efficient solutions. And this is a very much an unexplored space. And there was a first attempt to define what kind of an instance, a queasy instance would be, which is an instance that's quantum easy, but well, queasy for classical algorithms, so very, very sort of difficult or unpalatable for efficient classical algorithms. So for this, so definitions are just literally being built as we speak, but it's sort of, one has to think about how do we evaluate this instances and inputs. So one has to build a special type of pipelines where you have your input, you have your classical algorithms acting on these inputs, you have your quantum algorithms, a variety of them, acting on these inputs, and perhaps looking at the solutions in total, seeing that if your optimization problem is of such size that classical optimizers that you have, however well tuned, output garbage, there may be some more hope, and in general there are reasons to believe that quantum algorithms, quantum annealers, and QAOA type solutions will provide us with answers that are more biologically significant than those answers that are given by the classical algorithms. So I have just a bit of over a minute left. I'd like to leave you with some conclusions. So throughout this journey that is still ongoing, we've identified a number of interesting computationally intensive problems in pangenomics that can be efficiently represented in a quantum computing formulation. We've also identified several areas that will provide key insights on the practical potential of quantum computing for genomic and pangenomic data analysis. We found some remarkably efficient data encoding algorithms. We looked at assembly and pangenome graph, and tangle resolution problem in its QBO and QAOA formulation. Something I didn't mention here, but we really looked at phylogeny and building kind of phylogeny trees, so history of mutation trees for various sequences. So as you can imagine, this could be broadly applicable across the clinical spectrum. And the kind of a preliminary conclusions that I can make now is that there are problems in genomics that are very important, but we are indeed computationally limited. When quantum hardware becomes really good, quantum solutions will be adopted. And there is a lot of opportunity for young people, for new aspiring scientists, to think about problems, identify symmetries, structural features of these problems that will lead to vast simplification of their representation and the corresponding quantum algorithms, optimization algorithms that solve these problems. So as I said, there are many different problems in this space. We're just beginning to explore this exciting area. So if you have any questions, come and find me and talk to me. Thank you.